Okay, hi guys. I just wanted to show you this thing I found with the Rodin Dial and the ratios of thirds, halving, and the phi ratio. Here's the prime point of unity found from doubling circuits, this point here. Here I'm showing that if you create a circle from the prime point of unity, touching the prime point of unity and the outside of the circle here, and then replicate that again and again, you can see that it's very, very close to a perfect third, but not quite, showing with the circle here. That's the ratio found, so it's 0.043 odd different to perfect third, so about 4% discrepancy. Same thing here, I just put a 6-sided geometry in here, embedded another hexagon inside that hexagon, and it gives me this point here, which is this much different to the final point of unity. Again, 1.0418. Last one was 1.0437, so very similar, very, very close to the final point of unity. Okay, I've got other stuff here, but it's not so important. Well, here's the phi spiral, as Nazim shows. I built the phi spiral from a Fibonacci sequence geometry, and so it's a Fibonacci spiral, so it's approximating the phi spiral. So if I had done this more and more accurately before I created it into a circle, it'd be more accurate. But so at any one point, you can just stop creating the curvature from the ratio 1 to 0.618 to just 1 to 1, makes a circle comes back on itself, creates a boundary around the phi spiral. Phi spiral isn't approximating the center, it's approximating this prime point of unity, off center approximately thirds. And the difference I got there, which may be just how accurately I've made this particular spiral, is very close, again 1.048. Okay, so this is the second part that I wanted you to see, which is the main part. All I've done is I've started with the baseline of 1 to 1, so these three diameters of these circles are the same unit length. I've then just replicated that circle and reduced it by thirds, and in this case halving, and in this case phi ratio 0.618, and you end up with a specific angle and length created from that ratio to the baseline. And here they are, they're the degrees, and the lengths. Okay, the first thing I found was that I took C, the length taken from the phi ratio angle, divided that by the halving ratio angle length. So there it is there, C and B as circles, C and B, C divided by B, 1.376. And then all I did was I thought, well, how close is the center of this circle to the prime point of unity point? And so there it is. Should blue. And that's how close it is. It's not exact, so there's a difference there. But as you can see, it almost exactly inscribes the hexagon inside the Rodin dial. And believe it or not, this is actually extremely close, even though these points are off. All of them are slightly off from the exact hexagon and the exact center. If you actually try place a circle in here that's exactly on these points, you can see how far off it actually is from being a perfect hexagon. So no matter which way you try to do it, starting a perfect circle from this point, if I choose this point, see how far off it is from the top and bottom points, and I try this point, see how far away from this from the side points and the bottom points. Try these bottom points, you can see how far off it is from the midpoints and the top points. So it's not an exact equal hexagon anyway. As you can see, this diamond is way out of shape. So really this circle is about as close as you'd ever get to being exactly on these points. But that was pretty interesting. So that's just the ratio between C and B here, by ratio angle length and halving ratio angle length. So I got this number, and I thought, well, what if I took 0.33333 from it? In other words, if I took a third from this number, this new ratio I've got between halving and pi ratio, stick that into a calculator, and take thirds from it, take a third, and lo and behold, 1.043048. So where have we seen that number before? .0437 for hexagonal ratio 1.0418, and my one is 1.0430. So within thousandths of a percent accuracy. So I thought that was interesting. So what I did here is, started with a baseline of 1 to 1, reduced by thirds, and just put the new circle touching the original circle, and I could do that on and on and on and on. So I could reduce this circle by a third, put it here, diameter to diameter, touching diameter, so to speak, and then just go on and on and on forever towards this asymptotic point. So thirds gives me a specific length from the baseline this asymptotic point. So this point, so now do it again with halving. So this circle, so this circle is half of this circle, and I could again keep doing that and that forever, keep approaching this asymptotic point. And now I've got pi ratio, same thing again, 0.618 of the original, 0.618 of that one. And as you can see, the asymptotic point of thirds exactly correlates with the top of the circle of the first iteration of halving here, and the asymptotic point of halving exactly hits the top diameter circle point of the second iteration of pi ratio.